Watching this video, which is part of the minisymposium on Stein's method in computational statistics for the MCQMC conference 2020. So in this talk, what I'll be talking about is how to construct control variates in a scalable and efficient way using stochastic optimization. So let's start with setting up a little bit of notation. So the main problem will be that of computing some integral, and this will be of a function which defined on Rd and is real valued. And I'll want to compute such integrals of functions against an arbitrary distribution P. So what are potential applications of this that I'm mostly interested in? So some of these might be marginalizing out some variables. I also work in Bayesian statistics, so there you want to compute posterior moments or model evidence, etc., etc. And these can all be written as such integrals, obviously changing what f and p are depending on the case. Now the problem is, of course, that we can't estimate them, we can't compute them in closed form, so we need to estimate the integrals. Now, a very obvious way of doing that would be using a Monte Carlo estimator, and this won't be news to anyone at this conference. So what you do is you just sample some realizations from the distribution P, and then you use this sum of function values at these points. Now the question, of course, is how well will this work? Well, this can be quantified using the central limit theorem. So the central limit theorem, it tells us something about how good this estimator will be as n grows, n being the number of samples. And usually the rate of convergence will be square root of n. And the constant, or what you can think of as the constant, will be the variance of this central limit theorem. And in this case, this variance happens to be the variance of f under the distribution P. So similar results can also be obtained for other Monte Carlo methods. So I could do this for MCMC. I would get a slightly different central limit theorem where the variance will look more like this, where this now incorporates something about the correlations of the Markov chain. Now we're at MCQMC, so of course I should mention QMC, and of course there are similar central limit theorems for QMC, again allowing us to understand the performance of the QMC estimators. So in all of these, the kind of variance of the central limit theorem is a way of measuring the complexity of your function and how hard it will be to estimate the integral of this function relative to the distribution P. Okay. So now, if my function is complicated in this sense, then my estimator will tend to be bad, and if it's simple in that sense, then it will be easy to estimate it. So one idea, and that's the idea behind control variates, will be to try to modify your integration problem to make sure that you're trying to integrate a function which is easy in the sense of the variance. So in particular, in my talk, the definition of a control variate will be any function g such that the integral of f minus g is exactly the same as the integral of f, or namely, I could also say that the integral of g is equal to 0. And the variance of f minus g is much smaller than the variance of f. So let's imagine for a second that I can find such a function g. Then obviously a kind of straightforward way of improving my estimator of the integral would be to estimate the integral using the following sum. So instead of a sum of f values, you just do a sum of f minus g values. And now the quality of this estimator will depend not on the variance of f, but on that of f minus g. So our second criterion here above will guarantee that the estimator will be much better at estimating the integral. And also, the very first criterion guarantees that integrating f minus g is the same thing as integrating f. So in particular, this is a valid estimator for the integral of f. Now in this talk, what I'll do is I'll I'll go through how to construct such control variants, and in particular construct them for some potentially fairly complicated distributions P. So for example, what I'm interested in is when P is a posterior distribution. So I want to be able to find the function g which integrates to 0 against an arbitrary posterior distribution. And once I've done that, I'll try to explain how to choose such a function g to guarantee the second criterion, namely that the variance of f minus g is smaller than that of f. So how do I do that? Well, this symposium is on Stein's method, so obviously I'm going to use Stein's method. So let me just give a quick recap of what Stein's method is, in case you haven't been through the other talks. So Stein's method is a way of characterizing an arbitrary probability distribution, P. So in this case, you could think of P as being my posterior distribution against which I want to integrate. Now the way you do that is usually using two things. There's a Stein class, which is just this class of function u, and a Stein operator, which is just an operator on these functions. Now we say that these two things, the Stein class and the Stein operator, characterize the distribution P if the following holds. So whenever I apply the operator to the function u, it will integrate to 0 if and only if I'm integrating against P. So you can think of this as a way of representing P. Now, usually this is used for things like kind of theoretical results in probability theory, but here what we'll do is we'll use it in a computational way. So in particular, we can use it to construct control variants. So how do we do that? Well, all we need to do is take any function of the form SU, and this will now, by definition, be a valid control variant in the sense that it integrates to 0. In particular, I can get a whole class of functions of this form. So for any u in the space big U, I can take a function of the form SU, and that will integrate to 0 and therefore be a valid control variant. Now, there's obviously the question of how do you find such a function space U and a Stein operator? And here I've just assumed that we have access to these, which will be the case for most problems, because there's been a lot of research in Stein's method. But let me now try to explain to you how, well, or at least give you some examples of when we do have access to these. So the simplest example is if we want to characterize a normal 0, 1. So in this case, the Stein operator will be something very simple. You just take u prime minus xu. That will be a valid Stein operator. Now, obviously, there's going to be some conditions on functions u. Namely, they have to be absolutely continuous and satisfy this condition. And this was the very first characterization I proposed through this method, so in this original paper by Charles Stein. Now, obviously, this is not so useful for us because most of the time we will not want to compute integrals against Gaussians, but maybe against slightly more complicated distributions. So let's see how we can generalize that. Well, one way to generalize it is through something called the generator approach to Stein's method. And here the idea is simply to use the infinitesimal generator of a certain Markov process as a Stein operator. And using properties of these infinitesimal generators, we know that we can use these as Stein operators. So in particular, the example that I'll be using in this talk will be that of the generator of a Langevin diffusion. So I've just written them here. So what I do now is I just take a function g of the form Stein operator applied to u, and this will integrate to 0 by construction. So in particular, this will be true for a very large class of distributions, and I'm hiding some of the technical conditions. So exactly in the same way as for this normal case, there will be some kind of conditions both on u and on p, and I've chosen to hide them just for simplicity, and you can find them in the papers. But one thing that's quite interesting is that this operator, in order to evaluate the operator, you only need to know about grad log p rather than p itself. And that's particularly useful because it means that we don't need to have the normalization constant of p. And that's really useful for problems like in Bayesian statistics where you do not have necessarily access to those. So that's why it's quite general in the sense that you can use it for a lot of problems. So let's go back to where we were. So if you recall, I had this objective for finding a control variate, which was find a function which integrates to 0, and find a function that such that f minus g has smaller variance than f. So I've told you how to do the first step. So all you need to do is take any function of the form su, and that's a valid control variate. And so this is using Stein's method. Now there's still the question of how you kind of satisfy the second criteria. And there's quite a few things you could try. So one thing you could try is just taking the control variate to be an approximation of the function f. So that would allow the variance of f minus g to be smaller than the variance of f. But actually we don't need g to be equal to f everywhere. We only need it to be the case in areas where we have high probability. So something like minimizing directly the variance of f minus su sounds perhaps like something more sensible. So how would we do that? So we look for a function u in the Stein class such that the variance of f minus su is minimized. And there's obviously a couple of approximations that we have to introduce here. So one of them will be, usually you can't solve this over the whole of u, so u being the Stein class. So you have to look in some parametric subspace. So this might be the class of polynomials or some kind of kernel interpolant class. And then you optimize over the parameters. The second approximation is that most of the time we can't evaluate the variance in a closed form. So now another thing we might want to do is use some of our function values in order to estimate this variance. And otherwise, more generally, so in the literature, a lot of control variants for Monte Carlo methods fall within this general framework where you just use different kind of combinations of Stein operators, parametric class, or estimates for the variance. So let me recall a couple of them. So two main classes, at least in terms of parametric space, are polynomials and kernels. So I've listed a range of papers that consider these. And so what happens is that in order to minimize this variance, or the estimates of the variance, you usually have to solve some kind of linear system to find the optimal parameter values for these control variants. Okay, so here's an example of the kind of performance that we can expect. So let's look, for example, at the Gaussian peak function here. So here, these 6 functions, they're the Genz functions. So they're a class of test functions which tend to be quite challenging for numerical integration, mostly because they have some kind of weird properties like a lot of oscillations, maybe they're discontinuous or something like that. And but they do have the advantage that you can compute the integrals in closed form. So we can use them to kind of test how good each of our methods are going to be. So let's look at the Gaussian peak. So in this case, the first column is just an estimate. It's just the error, the mean absolute error for Monte Carlo. So just using a standard Monte Carlo estimator. Now there you get an error which is of order 10 to the minus 3. And the next column is if I use a polynomial of order 2 control variant. So here you can see the mean absolute error decreases a little bit, but not terribly much. Now, if I use a kernel-based control variant, here the improvement is quite significant. So in particular, you gain 2 orders of magnitude in terms of mean absolute error. And again, I can do the same thing by, for example, combining these, and I would get the last column, where you gain a little bit more again. So really here you can see, using these control variants, you can gain something like 2 orders of magnitude in terms of error, which is quite significant. So in this setting, I forgot to say I had about 1,000 samples and I was in dimension 1, so this is still a fairly simple problem. Now the thing that I've kind of hidden from you is that obviously computing these control variates can be actually quite computationally expensive. And this has often prohibited the use of these control variates for more challenging problems. So in particular, more challenging, what I mean here is problems where the number of samples, or perhaps even the dimension of the integration problem is much larger. So here I've written the computational complexity for either polynomials of order k control variates or kernels. As you can see, whenever m or d grows, this will blow up really quite fast. So what I and a couple of collaborators proposed in the following paper is a way of making these methods a lot more scalable using stochastic optimization. So obviously I should mention there's another talk on control variates in this symposium by Leah, and there she will give another way of making control variates more scalable, which is compatible with what we'll be discussing in this talk. So the way that we'll implement this is by using stochastic optimization, and we'll frame the problem in a convenient way such that we'll get nice properties from it. So the way we'll do this is by looking at this estimate of the variance plus some penalization for the parameters. And we'll just decide to minimize that. So the estimate of the variance will just be just a Monte Carlo estimator. And what we can do is just do stochastic gradient descent on this objective. So we just initialize at some parameter values theta 0, and then follow the gradients in order to minimize this. So here, for example, a convenient way to choose theta 0 would just be to pick all to be 0. For example, in the case of polynomials, that would mean not having any control variate. So it would initialize at no control variate, and then just follow down the gradients of this objective in order to get a better and better control variant. So why is this useful? Well, there's a couple of reasons. So the really main reason is computational cost. So by framing the problem in the way I've done, first of all, the cost of computing these gradients will usually be linear in the number of parameters. Whereas previously, if I was solving linear systems, it was cubic, which is a lot more challenging, especially when I have a lot of parameters. The other thing is that I don't need to look at all the samples at each iterations. So here, I insist now on the part of stochastic for stochastic gradient descent, which means that we can use subsamples, we can subsample the gradients and still converge under some guarantees, so under some conditions, sorry. So that's particularly useful in the sense that you don't need to look at all the samples at each iteration, and you can still get some nice control variance. Finally, because of the way we framed the problem, we can really stop the stochastic gradient descent procedure at any point in time and still get a valid control variance. That means that if I stop after, let's say, t iterations, the parameter estimate that I'll get will still be valid in the sense that SU of theta t will still integrate to 0. It might not be the best control variant, but it will be a good one. At least as good as you could have done given your current, the computation you've done so far. Whereas in the case of solving the linear system, usually you have to wait for the whole system to be solved before you can actually have a valid control variant. So let me show you what this does on a simple problem. So here I'm integrating some function which is quite simple, so it's just a sum of xi's, and I'm going to integrate it against the normal 0, 1. So let's start by looking at the left-hand side plot. So here I'm comparing different methods by the error that they get, so that's the y-axis, relative to computational time spent, so that's x-axis. So first of all, the green line, the horizontal green line, tells you the absolute error that you get if you use a Monte Carlo estimator, so no control variance. That's obviously not so good in this particular case, but the advantage of it is that it's really cheap. So the computational time is basically 0, which is the vertical line, dotted line. Now, in this case, I've used kernel-based control variance, so the red line is now going to be the performance of the kernel-based method. And as you can see here, you get something which is pretty much 0 error, but it costs you quite a bit more, so something like 0.25 maybe seconds. Now all the blue lines are our methods, so the method where you minimize the variance using stochastic optimizations. And each of the different lines are different runs of this, just to show you a bit the variability in the results that you can get. The blue dots are the kind of average performance. So here what you can notice is that obviously it takes more time to get the error to be quite small, but if I look at any of these dots before the vertical red line, I can see that I can still get a reasonable absolute error with a lot less computational cost. So I could stop at that iteration and still get a reasonable control variance, which is quite useful. Now perhaps on this problem it's not so useful because we have a small number of samples and we're only in dimension 5, so we have, I think, 500 samples. However, if you look at the other plots, now you see the performance for when I increase the number of samples or the dimensionality of the problem. And as you can see, the gains can really be quite drastic. So you can get the same error as or pretty much the same error as the exact method, but really at a fraction of the total computational cost. So that was all about computational cost. So you can see that our approach has really quite significant advantages. The other advantage is that it's quite flexible. So in particular, if I have not just one pair of Stein operator and Stein class, but multiple pairs, what I can do is create more interesting classes of control variants. So I can just take a linear combinations of these control variants, and that's still a valid control variant by construction. And so I can use things like polynomials, kernels, anything, any parametric class, just to get something a bit more expressive that might be able to approximate the integrand better, or at least make the variance of f minus the control variant as small as possible. One advantage is that whenever we choose linear classes, so linear in the parameters, so that would be the case, for example, if I took polynomials or kernels, then I can guarantee convergence because the optimization problem will be convex. And that's really quite useful. However, there's nothing that forces me to take a linear class, so I can take something like a neural network, and that would still work fine. But obviously the optimization problem might be a bit more challenging. So let's have a look as to how useful that can be. So my last example now is a Bayesian logistic regression example in dimension 61. And here I'm just increasing the number of samples and looking at the impact on the mean absolute error and on the computational time. So let's have a look perhaps. Well, first of all, the baseline, the black line, that's just Monte Carlo estimator. And then I can look at, for example, the yellow lines. So the full yellow line is if I use both a kernel and a polynomial control variates. And the one that's full is if I use SGD, and the other one, the kind of dotted one, is if I solve the linear system. So on the left-hand side plot, you can see that both minimize the absolute error roughly at the same speed. Usually the linear system is a tiny bit better, but really negligible. And that's mostly because I've not fine-tuned my optimizer very well. However, on the right-hand side plot, what you also notice is that the computational time really grows super fast for the linear system, but the kernel and the stochastic optimization method, the computational cost doesn't increase too quickly with the number of samples. Now, the best performance that we got was when we used multiple kernels, so different kernels, and a polynomial, and that's the kind of teal line. So you can see here, you can get a really small mean absolute error, and the computational time is not too big. And in fact, that does even better than the neural network, which is the red line, in terms of mean absolute error and also computational time. And in particular, the advantage of this multiple kernel and polynomial control variant is that since all of these are linear classes, then I'm going to get a convex problem. And something that's a bit hidden in those figures is the fine-tuning of the optimization methods. And actually, for these convex problems, it's a lot easier to do than for these non-convex problems where I'm using something like a neural network. So that's it. I hope that you've enjoyed this talk. So in summary, Stein's method is a very powerful tool for computational statistics, and in particular for constructing control variates. In this talk, what I try to highlight is how this general approach can be made to be quite flexible and scalable, so that we get really quite expressive classes of control variates, which can tackle quite challenging problems. And one remark that I thought I should make is that although I presented the case where the objective is the Monte Carlo variance, you could do the same thing for MCMC or RQMC by changing the objective that you're minimizing. So thank you very much for listening, and if you want to find out more, you can have a look at this paper, which is available on arXiv. Thank you very much.